In this lesson, we're going to go over Newton's method. Newton's method is a numerical technique that's used to approximate solutions to equations like f of x equaling 0. Graphically, f of x equaling 0 is where the graph of y equals f of x crosses the x-axis. So if you have a function whose graph looks like this, then you have 1, 2, 3 solutions to f of x equaling 0 for this graph. Now the advantages to Newton's method is that it's easy to use, it yields rapid convergence to the solution, and it can be easily used to accurately approximate the nth roots of numbers. So you can very quickly approximate, for example, the cube root of 2. Disadvantages to Newton's method is that it doesn't work for every function, but it does work for most commonly used functions. And there are cases where it yields slow convergence to the solution, but there are techniques to overcome this problem, and once again it's rare to run into those cases. Now let's go over the derivation of Newton's method here. So let's consider the graph of a function that we have here. This blue curve is a function, and we want to obtain the solution right here, C, to f of x equals 0. Right there at C, that is our solution to f of x equaling 0. So in other words, f of the number c is exactly equal to 0. And we want to find c. So what we'll do is this. In Newton's method, you start with a number that is close to c. So you can, somehow approximate c. Perhaps you know that f of 5 is positive and f of 4 is negative, so your solution would be somewhere in between 4 and 5. So you start out with an initial guess, like x0. You go up to the curve and draw a tangent line, as we have here. That brings you down to another point right here on the x-axis. We'll call that x1. Then you repeat the procedure. You go up to your curve, draw a tangent line, and come up with another number, x2. Notice how by doing this we've gotten closer to our actual value of c. And we keep doing this. Up to the curve, draw a tangent line, come down. There's our next approximation to c. And notice how we've gotten still closer. If we keep doing this, we will keep getting closer and closer to the number c. Now, we have to come up with an algorithm to evaluate these numbers, x1, x2, and x3. Well, it's actually fairly easy. We need to find the equation, first of all, of that line L right there. Well, notice that the line L passes through this point, and that is the point x0, which we assume that we know, f of x0, that's that point right there, and the slope of this line is given by just the derivative of f at x0. So here is a point the line passes through, and here is its slope. So the equation for L is going to be there's our equation for L. This is the slope m right here, and this is a point. The point the line passes through is x0, f of x0. So this is your point slope form for the equation of a line. Now we want to find where L crosses the x-axis, and that's going to be our x1. So to find where L crosses the x-axis, we set y equal to 0 and solve for x. So if we set, then we get and now we have to solve this equation right here for x. So we'll divide the f prime, that's a number that we know, divide it underneath the f of x naught, and then add the x0 over to the other side. And what we'll get is and this value right here is where the line L crosses the x-axis. So that is our x1. This value is x1. Now, if we want to solve for x2, we do the exact same procedure, but with x1 in place of every x0. So to find x2, all we do is replace all the x0s with x1. So we'll get x2 is x1 minus like that. And then x3, we just replace the x1s here with x2s. And that is Newton's method. Or in other words, in general, and this is Newton's method right here. So Newton's method is what we call an iterative method. Notice that we start out with next 0. We put it in here for the xn's right here, and that gives us back x1, so we get a number back. Then we take that number and we put it back into the right-hand side. So we put x1 back in here for all these xn's, and we get back x2. And then we take that number and put it back in to the right-hand side and get x3. And as we continue that process, we will get closer and closer to our actual c value, which is the solution to f of x equaling 0. Let's take a look at the formal statement of Newton's method and then some examples. For Newton's method, we want to approximate the solution c to f of x equaling 0, and we do the following. We begin with an initial guess x0 of the value c. A graph may be helpful to do that. Then you determine a new approximation, x1, using this formula. So you put x0 in for the xn's here, and you'll get back x1 on the left-hand side. Then you continue updating xn by repeating step 2 until a desired level of accuracy is achieved. And one way to do this is to continue updating until the difference between successive iterates is less than some small number epsilon that you want. Perhaps it's 0.01 or 0.001, whatever level of accuracy is desired. So let's take a look at an example. In this example, we want to approximate the solution to x to the 5th plus x minus 1 equals 0, beginning with an initial guess of 1.5. And we want to perform 4 iterations of Newton's method, so we will eventually find x4. So remember Newton's method, we have to iterate this function. So this is the function that we have to set up. We'll call that g of x. And what we're going to do is we're going to put this into our calculator, and I'll show you how to iterate this to obtain x1 and then x2 and x3 and so on. Now this function here is going to be x minus, our function f is x to the fifth plus x minus 1 divided by, and our derivative is of course 5x to the fourth plus 1. So this is what we have to iterate. So to do that, it's easiest to use a calculator like the TI-83 or TI-89. So I have a TI-89 emulator right here, and I'll show you how to do this. What you can do, turn it on. Now normally you'll probably see your home screen right here when you first turn it on. We're going to put this function g into the y1 register of our calculator. So we are going to press green and F1, and this is where you enter functions. So we want to enter this function in for y1, so we'll type in x minus x to the fifth plus x minus 1 and then hit enter. And there our function is entered into y1. Now I'll show you how to do this on a TI-83 in a few minutes as well. Let's just do this on the 89 first. Now what we're going to do is we're going to go back to the home screen, and we want to evaluate x1. And here's how we'll do it. This function is now stored into the y1 register of our calculator. So x1 will be y1, or g, of 1.5, which is x0. So we simply have to evaluate y1 of 1.5, and that'll give us x1. So to do that on the TI-89, and I'll show you how to do this on the 83 soon, you just have to literally type in y1 of, y1 of 1.5, like that. Hit enter, and there we have x1, 1.1924. Now if you want more decimal places than that, which I would advise, you can change the mode setting on your calculator. I'm going to show you how to do that. Press mode, and we want to set our display digits. I have to cursor down, over, and I'm just going to set it to float E, and then hit enter. And that'll give us more decimal places. So now I'm going to hit enter again. I'm going to clear that out. y1 of 1.5. And there we have many more decimal places of accuracy. So we would say here that x1 equals 1.19239. I'm going to go out to 1, 2, 3, 4, 5, 6 decimal places. Now x2 is going to be y1 of x1, which is this number right here. Now watch this. Instead of typing this number in up here in place of that 1.5, watch what we can do. You clear that out. You see our number x1 is right here on what we call our stack. It's in position 1 right here. So we just have to type in y1 of, now you see that little ANS down here? That will recall the previous answer that's on your stack. So press second, that minus button there, and you see ANS of 1 appear. Close the parenthesis. Now it will evaluate y1 of x1, which is right here, to many decimal places. So it will give you a good degree of accuracy. And hit enter. and we get 0.95 806 1 2 3 4 5 6 8, taking it, rounding it to 6 decimal places. And now to find x3, all we need to do is hit enter. You see, this is already on the stack, y1 of answer 1, so now the calculator will take this number right here and put it in place for our x right here and evaluate y1 of that number. So we just have to hit enter again. So that's what's so nice about using the calculator here. So now we just hit enter again. There is x3. 0.811258 to 6 decimal, rounded to 6 decimal places. And finally x4, we just have to hit enter again because x3 is sitting right here on the stack. The ANS1 will take that number, put it right in place for the answer 1, and evaluate y1 of that number. So we just have to hit enter again. And there is finally our x4, 0.759879, rounding to 6 decimal places. And let's check it out. Right here's the graph of the function, and right there is where we cross the x-axis. That is our solution to x to the 5th plus x minus 1 equals 0, graphically right there. And yeah, it does look like that number is around 3/4 or 0.75, and we came up with 0.759879. Now watch what happens if we were to keep hitting enter. These numbers would eventually settle down and stop changing. And then that would be our answer, accurate to however many decimal places we have displayed on our calculator. So watch, if we keep hitting enter here, eventually they will stop changing. So there's x5, 6, 7, 8. So 7 and 8 stop changing. So we see that x7 equals 0.754877666247, and that doesn't change anymore after we keep applying Newton's method, if we were to keep applying Newton's method. And so that is our answer, accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal places. Right there it is on the x-axis. Let's take a look at doing this with the TI-83 just to show you how to set it up. Close out my 84 here. There we go. 89, I mean. There we go. Now my emulator for the TI-83 is a little smaller, so here we go. So the same procedure. You have to press the y equals button and store this function into the y1 register of your calculator. So now the x button on the 83 is the xt theta n button. So x minus, make sure you put your numerator and denominator in parentheses. Alright, so there we go. We have our function stored into y1. Now what we have to do is go back to our home screen, hit second mode for the quit right there. Now we have to enter y1 of 1.5. So to do that on the 83, you have to press the vars button and go over to yvars and hit number 1 for function and number 1 again for y1, and then you can evaluate y1 of 1.5 and hit enter, and there you go. Now to evaluate y1 of this number again, you have to go vars yvars 1 1, and then of, and on the 83 it also has an ANS right above the minus, the negative button right there. So second ANS, close the parenthesis, and there you go, 0.958068, which is what we have down here. And then you just keep going. I'll do it 2 more times. Yvars of answer. There you go, 0.811258, which is what we have down here. And then finally, hit enter of second ANS. And there we go. This is the same as what we came up with using the TI-89. So that's how you can use a TI calculator to do these problems very easily. It's basically you just need to enter this function right here. You just have to enter this into the Y1 register of your calculator, take your initial guess, and evaluate Y1 of your initial guess, and then just take that number and evaluate Y1 of that using the ANS feature of your calculator, and then you just keep going. Let's take a look at another example. In this example, we want to approximate the solution to x squared minus 2 equals 0, beginning with an initial guess x0 equals 2, and perform 4 iterations of Newton's method. Now notice that by solving this equation, what we're doing is we're solving this, and we start, the solutions to this are going to be, and then taking the square root of both sides, we get x is going to be plus or minus the square root of 2. Now, since we're starting with an initial guess of positive 2, we're going to be approaching positive the square root of 2 by using Newton's method. So really what we're doing here is approximating the square root of 2. Here we have the graph of x squared minus 2. Where it crosses the x-axis, those are our solutions to f of x equaling 0. So here we have positive the square root of 2, and over here is negative square root of 2. Now by starting with an initial guess of 2 over here, Newton's method will converge to positive the square root of 2. If we started with negative 2 as our initial guess, we would converge to negative the square root of 2. So let's start Newton's method now. So we're going to enter this function into our calculator, into the Y1 register. We want to enter Newton's method, so that's, remember, f of x, x minus f of x over f prime of x. And in this case, our f of x is x squared minus 2, so this is going to be so there, that's the function that we want to iterate. X minus x squared minus 2 divided by 2x. Let's put this into our calculator and begin iterating it. So here we are, we're going to enter this into the Y1 register of our calculator. So we'll type this in as x minus, be careful with parentheses, and then divided by, now the 2x has to be in its own set of parentheses, so be careful with that. 2 times x. The times symbol there is optional. Hit enter. There is our function entered into the y1 register. Now we'll go back to the home screen, and we will enter y1 of 2. And that will give us back x1. Now when we hit enter, we get 3/2. Now let me point something out on the TI-89. If you want to get 1.5 here, normally we want a decimal answer here. If you look on the TI-89, there's a little approximation symbol right down here. You can hit green and then enter, and that will give you a decimal representation instead of 3 divided by 2. It depends on the mode that your calculator is set in. So if you get this, 3 divided by 2, and you want a decimal representation, you can do this. So here we have y1, and we need to hit green and then enter, and there we get back 1.5. So that is x1. Another way to do that would be like this. If you type in 2 and you put a decimal right after it, then when you hit enter, the calculator will assume, since you have a decimal in here as one of your inputs, that you want back a decimal form, and then hit enter and you get back 1.5. That's not really an issue on the TI-83, but on the TI-89 it can be. So what we found now is that we started with x0 equaling 2. We found that x1 is 1.5. Now we need to find x2. So we'll enter now into our calculator y1 of the answer ANS. So second, that minus button down here, you see we have y1 of ANS1 up here now. That'll pull the 1.5 inside the parentheses, and evaluating that, we get back 1.467. So 1.4167, rounding to 4 decimal places. And then x3, evaluating that, we'll take that to 6 decimal places. You see we get 1.414216, rounding this to 6 decimal places. 1, 2, 3, 4, 5, 6, right? And then finally, let's evaluate x4. So we just have to hit enter again. And there is x4. 2, 3, and let's round that to 4 right here. 1.414214. Okay. Now, let's see how many times we have to keep hitting enter until this number stops changing. Let's see if we hit enter one more time. Oh, well, we see x4 and x5 are actually the same value, so x5 is also rounded to 6 decimal places, and so we already have a high degree of accuracy. So we already have accuracy out to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, out to at least 11 decimal places. Now, so this is our approximation, this is our answer to the problem, and that is our approximation to the square root of 2. On the calculator, let's just evaluate the square root of 2 just to check it out, that that's exactly what we found. So if we evaluate square root of 2, and I'll have to hit the approximation button here, so green, and enter. And yes, that's exactly what we have. Notice this was this value right here was one of our Newton method iterates. That was x5, and it's the same as x4. And here is the square root of 2, and we notice that they are exactly the same. So that's exactly what we found here by solving this problem, the positive square root of 2. Let's look at another example. Now in this example, we want to approximate the cube root of 10, beginning with an initial guess, x0 equals 3. And we want to perform 4 iterations of Newton's method on an appropriate function. Now you notice we're not given the function f of x for which we want to solve this equation. We're not given the f of x, so we have to figure out what f of x should be. Well, the function we're going to use is going to be x cubed minus 10 equals 0. You notice if we solve this for x, you take the 10 over, and then you take the cube root of both sides, you get x equals the cube root of 10. So that's the general rule. If you want to find the nth root of a, you can use Newton's method with the function x to the n power minus a equals 0. Because if you move the a over and then take the nth root, you get your nth root of a. So that's a rule to follow when you want to use Newton's method to approximate the nth root of a. This is the function you want to use. Now, I've seen some students make this mistake and don't do this. Some people will use the function x minus the cube root of 10 equaling 0. Well, of course, if you take the cube root of 10 over to the other side, you get x equals the cube root of 10. However, the problem with this is you're using a number that you want to find an approximation for in your equation, and we don't want to do that. So that's why we want to use this function here. So don't do that. So beginning with this equation, we want to set up our function. So we're going to enter this into our calculator. This is our Newton's method function. And our f of x is x cubed minus 10. So this is going to be and there's our function that we want to enter into our calculator and then iterate, starting with x0 equals 3. So let's get out our calculator. And in the Y1 register, we want to enter x. And there we go. X minus x cubed minus 10 divided by 3x squared. Just be careful with parentheses again. Now go back to our home screen. And we want y1 of 3. And be careful, you want the you may need to use the approximation symbol down here. If I hit enter here, it gives me back a fractional form, the exact value. So I need to hit green and enter. That will give me the approximation down here in case you're using a TI-89. Alright, and there's x1. So x1, let's take it to a few decimal places, 2.37037, and then it just keeps repeating, 6 decimal places. And then x2 So now we have to enter y1 of answer down here, ANS, so second negative, and then hit enter. So there we go. So that's x2, 2.173509 to rounded to 6 decimal places. x3, just have to hit enter again. There we go. There is x3, this number right here, rounded to 6 decimal places. And then finally x4, and there's our answer. That's what we wanted. We wanted to evaluate x4. And since it's so easy, let's keep going and see how many more iterations we need until this number stops changing. So let's see, that is x4, here is x5, and then x6, and so x5 and x6 are the same. So once we get to x5, which is and there we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 decimal places. It doesn't change anymore. And let's just evaluate on our calculator the cube root of 10 using the calculator and verify that we get this number back. So if we evaluate 10, now to do the cube root, you need to raise 10 to the 1/3 power, 1 divided by 3, just like this. So you have to enter in this in your calculator. You need the parentheses. So here we have it entered, and hitting enter, well, I need to hit green and enter to get the decimal form. Notice how it just gave me back 10 raised to the 1/3 power again. That's the exact value. So green and enter, 2.1544, and we see that the value the calculator gave us back for the cube root of 10 is exactly the same as the value that we got after performing Newton's method until our decimals stop changing. So that verifies that we really did find the cube root of 10. And so that concludes our discussion of Newton's method.